Okay, so I guess let's start. Our speaker today is Benoit Monin, speaking about randomness and ITTM. Please.
Thank you very much. Thanks to all of you for being here. So I'm going to talk about randomness and ITTMs. So some of you already saw most of the material of this talk, but I would like to get a few additional developments that I haven't spoken about yet in the end of the talk, which I believe are of interest. Okay, so first of all, let me introduce you the ITTM model. So infinite time Turing machines, they are just like regular Turing machines. So traditionally, we think of them as having three tapes: some input tape, working tape, and output tape. All the tapes are indexed by omega. They are omega cells. And just like regular Turing machine, there are finitely many states and finitely many transition rules, which allows you to move, to do some action, write or read, and move the head. So the difference with a regular Turing machine is that the steps of computation might be any ordinal. So at a successor step, if the ordinal is a successor ordinal, it behaves exactly like a normal Turing machine, right? But the difference is that after omega steps of, after all the finitely many steps of computation, then it continues to compute. So we need to fix some rules to determine the behavior of the machine at limit steps of computation. So the rules are as follow. The head goes back to the first cell. The machine enters a special state, which is called a limit state. So it tells the machine that it is at a limit step of computation. And the value of each cell equals the lim_inf of the value at the previous stages of computation. So basically, if the value in a cell converges, then it is a value of convergence. And if it diverges, then it is 0. So having this model, so what's the first question we could ask is, what is the equivalent of being computable for an infinite time Turing machine? So first, I guess a valid answer would be what we call with ITTM being writable. So a real X is writable if there is an infinite time Turing machine, so which starts, so here M0, it means, so the machine M starts with 0 on its input tape, so no oracle. And after some ordinal step of computation, it writes X on the output tape, and then it halts. So this means the machine enters a halting state at step alpha +1. And when it does so, there is X, which happens to be on the output tape. So we say in this case that the real X is writable. So the first question we could ask is which reals are writable? So to answer this, let me make a small definition here. We say that a class of real is decidable if there is an ITTM which halts and answers 1 whenever on the oracle X, whenever X is in the set, and it answers 0 if X is not in the set. So for any real X, the ITTM halts and then answers 1 or 0, deciding whether the real is in the set or not. So first theorem that the class of real coding for well orders is decidable. So using some any coding, computable coding you want. So basically the pair NM is in the real if N is smaller than N. So how do you prove this? So it's a proof sketch here, some sketch for some algorithm. So suppose you have on the input tape some real X which codes for some order. So you can assume the order is linear. Checking if it's not linear requires only a few what you have codes for a well order. Well, in the simplest way you could imagine. So you have the order in your tape. Basically, you look for the smallest element of the order. If there is no smallest element, then it's not a well order. You write 0 and you halt. Otherwise, you remove this element from the support of your well order. So if at some point you removed every element and every time you could find the smallest one, then in the end you had a well order, then you write 1 and then you halt. So this is a very simple algorithm, and it's not completely obvious that it is something you can do with ITTMs. Like, how do you look for the smallest element? Well, so this is where you, of course, take advantage of the fact that you have ordinal steps of computations. And you also need to take advantage of the fact that you have a specific rule which tells you if something does not converge. So to find the smallest element, this is this rule that you use. So you fix a cell in advance, like the first one, and you decide to write 1 on this cell. And the current element, so you define it to be like so far plus infinity, something which represents plus infinity. So your ITTM proceeds as follows. If you're in a successor state, you're not in a limit state. Then, well, you look for, as long as you're in a successor state, you look for looking at your order if you find some A which is smaller than the current smallest element. If you find it, you update the smallest element and you flip the first cell to 0 and then you flip it back to 1 again. So in the end of all the omega successor state, like omega first successor state, you enter a limit state, and then all you have to do is check the value of the cell that you flipped, you switched back to 0 and 1. So if it is 0, it means, well, it was flipped back and forth to 0 and 1 infinity often, and then you don't have a smallest element. Otherwise, well, you have the smallest element. Otherwise, there is a convergence value. The cell is 1, and the smallest element currently recorded is actually the smallest element. So, as a consequence of this, well, the class of reals which code for well order, it's a decidable class. You can decide whether any real codes for a well order. In particular, every pi11 set of real is decidable. And also every pi11 set of integer is writable, right? Because you can simply enumerate all the recursive functions which codes for which codes for some orders. Then you can check if these are well orders or not, and using this compute any pi11 set of integers. In particular, clean is O. So basically, you can compute clean is O, and with clean is O, any other pi11 set of integers. So, omega-1 steps of computations are enough to write any pi11 set of integers. But there is no bound on the ordinal step of computation an ITTM can use. So assume that so you can design a ITTM machine which writes clean is O, but once clean is O has been written, well then it's on your on some tape, and you can use it to again write clean is O relative to clean is O using the same process, and so on. So the question is, where does it stop? Because there is no bound on the ordinal step of computation. So it's, however, not so difficult to see that whatever an ITTM does, it does it before stage omega 1. So if it does it after stage omega 1, well, it's necessarily something which has been done before. So to see this, well, you use the fact that the configuration of an ITTM is given by its tapes, 3 tapes, its current state, and the position of the head. And whenever you're at a limit step of computation, then these two, the state and the position of the head, it is the same. So let me introduce here this notation that I'm going to reuse. C alpha is some encoding of whatever is in all the 3 tapes of the ITTM at stage alpha. So I'm also going to use later C alpha with index I to mean whatever in the cell number I at stage alpha. So the Hankins and Lewis proposition that whatever an ITTM does, it does it before stage omega 1. So actually there must be a limit ordinal alpha such that C alpha equals C omega 1. And then whatever will happen from now on, starting in omega 1, it will happen, the same will happen starting at step of computation alpha, because the configuration of the ITTM is exactly the same. So simply, if you consider the value of the value of the tape, of some tape at step omega, so you have in green, I've put all the convergence value. So all the cells for which you have convergence. And all the other cells which are not green, the zeros, it's divergence. So you must have, because omega 1 is uncountable, you must have a countable ordinal alpha 0 such that all the convergence values are reached already. And then, well, with a simple argument, you can show that, so basically, you consider the first ordinal alpha 1 bigger than alpha 0, so that the first cell have diverged, has been flipped at least once between alpha 0 and alpha 1. And then alpha 2 bigger than alpha 1 is the next one, so that the 2 non-converging cell has been flipped between alpha 1 and alpha 2. And doing so, well, you have a supremum of countable ordinal, which is then countable, and such that, well, you only have 0 on cells which don't converge. So whatever an ITTM does, it does it before step omega 1. So something noticed by Hankins and Lewis. So we say that so some ordinal alpha is writable if there is an ITTM which writes some encoding some encoding of well order of omega with order type alpha. So a writable ordinal is an ordinal so that you can write a real which represents this ordinal. So it's very easy to see that the writable ordinals are an initial segment of the ordinal. And it's also, and there is necessarily a supremum of all the writable ordinal, which must be countable because you have only countably many ITTMs. So, and we call this ordinal lambda. Lambda is a supremum of the writable ordinals. So Hankin and Lewis noticed that there actually is an infinite time Turing machine which writes lambda on its output tape. But so it seems to contradict the fact that lambda is not writable, like it's the smallest which is not writable. But so the machine writes lambda, but then it does not halt. So the definition of being writable is we have to write you and then halt. So you can design an ITTM which writes lambda on the output tape, then doesn't halt, continue running, but leave that the output tape unchanged without ever halting. So this leads to the, so basically how the way you do it, so you consider some, so some universal ITTMU which runs simultaneously all the ITTMs computations for all the program. So at every stage S, you run this universal machine U for one step, then you compute the sum of all the ordinals which are currently on output tapes of programs simulated by this universal machine and which have halted. And then you write this sum on the output tape, right? So if you consider the smallest stage such that every ITTM have halted by this stage in the simulation of U, well then the ordinal you have must be bigger or equal to lambda. So this leads to the following definition. A real is eventually writable if there is an ITTM under step alpha, such that for every beta greater than or equal to alpha, the real is on the output tape at step beta. So it writes the real, then leaves the tape unchanged and maybe never halts. So and we make the same definition for eventually writable ordinals using some coding of the ordinal. So it's also not very hard to see that the eventually writable ordinals are an initial segment of the ordinals. And we write zeta for the supremum of the eventually writable ordinals. And Hankin and Lewis all noticed then that there is, in fact, an ITTM which at some point writes zeta on its output tape. And of course, as zeta is not eventually writable, then the output tape doesn't remain unchanged forever, but then will move. And well, the sketch proved to do so. So you call it, in this case, accidentally, so an algorithm which accidentally writes the zeta. So again, you run the universal machine for one step, then compute the sum of all the ordinals which are on the output tapes of programs simulated by US, and write this sum on the output. And if you consider the smallest stage such that every ITTM writing an eventually writable ordinal has done so by this stage in the simulation of the universal one, well then you necessarily have that the sum of all these is at least the smallest non-eventually writable ordinal. And this leads to the definition of being accidentally writable. So a real is accidentally writable if there is an ITTM and a step alpha, such that the real is on the output tape at this stage. And again, it's not very hard to see that the accidentally writable ordinals are an initial segment of the ordinals. And we write sigma for the supremum of the accidentally writable ordinals. So and what we have is lambda is strictly smaller than zeta, which is strictly smaller than sigma. So we now have to talk a bit about constructibility, since ITTMs are deeply connected with some initial segments of Gödel constructible universe. So here is a recall of the definition of the constructible universe. So you start with L of 0 to be the empty set, and then at a successor step, L alpha plus, it's basically all the subset of L alpha that are first order definable with parameter over L alpha. And at limit step, you take the union of all the previous steps. So it's been used by Gödel to build a model of ZFC. And it's basically all the sets, so the minimal model of ZFC, which contains all the ordinals that you consider. Like basically it's everything which you can construct iteratively. So, so with ITTM, so the connection with ITTM, the first connection that if alpha is a writable real, and x is a real which belongs to L alpha, then x is writable. And same for eventually writable and accidentally writable. Yeah. So basically, this basically uses the fact that somehow, to some extent, the function which to alpha associate L alpha is sort of computable. It's computable by an ITTM function which alpha associates some coding of L alpha. So of course, you only have you only work within the countable. So, but for the first few countable alpha, this is so. Actually, as long as you have an ordinal alpha written on some tape, then you can compute using some ITM the real which codes for L alpha. So I also need to talk a little bit about admissibility. So we say that an ordinal alpha is admissible if L alpha is a model of sigma 1 replacement. So basically what you need is whenever you have a sigma 1 formula phi, and whenever you have some set n in L alpha, if L alpha is model of for all n in big N, there exists z such that phi n of z is true, then you must bound for all the witnesses z must exist. So you must have z such that for all n in big N, there exists z in a bounded way, bounded by big Z here. So omega 1 ck, omega 2 ck, omega 3 ck, etc. are the first admissible ordinal. And the reason we care about admissible ordinal is because these are the ordinal step within which we can we have nice property which allows us to like extend notions of computation inside some L alpha instead of just inside L of omega. So it basically tries to mimic what's happening with normal computation. So when you have such a formula here, there exists n such that for all kids, so here an integer n, so that for any integer smaller than n, there exists an integer n, so that some computable property is verified. Then this formula is sigma 1. Well, because you have a bound. If for every integer smaller than n there exists a witness, then the supremum of all the possible witness has to be bounded. So of course, it's not necessarily true if we deal with infinite objects here. But so this is why, so the admissible, so the L alpha, when they are admissible, when they are model of sigma 1 replacement, this is where we can still do this trick, still consider such formula sigma 1. So the ordinal lambda and zeta are admissible. So if you consider some set in L lambda and a sigma 1 formula phi, and suppose that L lambda is model of for every n in big N, there is a witness z such that the formula is true, well, then you can write the following ITTM to show that lambda is admissible. So you first write a code for your set n here, and then for every element in your set n, well, you look for the first writable, for the first ordinal alpha n such that L of alpha n is model of there exists z phi of nz, and then you write alpha n somewhere. And once this is done, you write the sum of all this alpha n, and then you have a writable ordinal such that L of this writable ordinal is the bound that you look for. So and you can do the same with a similar thing with zeta. And you can do, so to show you a little bit how big are these ordinals, even though they are countable, So lambda is a lambdas admissible ordinal, and zeta is a zetas admissible ordinal. So suppose proof sketch. So suppose lambda is an alphas admissible for alpha strictly smaller than lambda. Well, then you design an ITTM which writes alpha, and while alpha is greater than 0, you look for the smallest. So while your encoding of alpha is greater than 0, you look for the smallest element of alpha and you remove it, and you look for the next admissible writable ordinal and write it to the E state. So once this is done, well, then you write the smallest admissible greater than all the one written previously. And then you have a contradiction. And you can do similar things for zeta. So you can continue. So an ordinal is recursively inaccessible if it's admissible and the limit of admissible. So these are already quite far up. But of course, you can show that lambda is recursively admissible, inaccessible. So this should be admissible here. This should be inaccessible here. And you can show similarly that lambda is a lambdas recursively inaccessible, and zeta is a zetas recursively inaccessible. And you can continue like this with meta recursively accessible and so on. So let's now see, try to give you a better understanding of these three ordinal lambda, zeta, and sigma. So the first thing, so it will be a bunch of lemmas, so which will give us very nice properties on this pair of three ordinals. So record here the notation Ci of alpha. So it means the content of the cell number I at step alpha. So fix any cell. So if the sequence of the values of this cell converges at step lambda, so if the sequence Ci alpha for alpha smaller than lambda converges, then it has to converge also for, so the value cannot change for any further step of computation. So for any further step of computation, well, the value remains the same. So to see this, well, suppose that your cell converges, and suppose it converges to 0. So and let beta be the smallest, such that the cell has reached its convergence at step beta. Well, then you can design the following algorithm. For every ordinal alpha bigger than beta, so beta is writable, you can write it, and then enumerate the ordinal that some ITTM can write, check if they are bigger than beta. So you still with your universal machine. So for every alpha bigger than beta, well, you simulate a run of the universal Turing machine for alpha step. And then if you find that the value of the cell number I is now 1, at some point for some ordinal between beta and alpha, then you write alpha and half, right? So it cannot be the case that if the value converges, it cannot change beyond some writable ordinal, because if it changes back to 1, from 0 to 1 after that, well, then you could write this ordinal. You can recognize it and write it. So this is a nice argument, well, to show that whatever converges at lambda, well, it cannot change its value at a further ordinal up to sigma. So, and you can do something similar between zeta and sigma. So this is the theorem from Welch. The whole state of an ITTM at step zeta is the same than its state at step sigma. So actually, remember the ordinal omega 1 before, so the argument to say that whatever happens at the configuration of the machine at step omega-1 should be the same as at some previous countable step before. So actually, this already happened between zeta and sigma. So whatever an ITTM, so whatever is the configuration of an ITTM at step sigma, it is exactly the same configuration at step zeta. And then if an ITTM hasn't halted before, then it will enter some infinite loop between zeta and sigma and so on. So, and this similar as before. So these are lemmas similar as before. So for any cell I, so if the value of the cell converges up to zeta, well, then it cannot change between zeta and sigma. And similarly, if it diverges, then also it has to diverge. So if it diverges below zeta, it has to diverge below sigma. And you prove that in a similar way that has been used, well, in a similar way that has been used here. So maybe I'll do the first, yeah, I'll explain you this one. So if you suppose without loss of generality that value, so it is actually very similar. So if the value of a cell converges to 0 below zeta, right? So you write beta is the smallest so you consider the smallest ordinal so that you have the value of convergence. And this ordinal, it is an eventually writable ordinal. So you have an ITTM which writes different versions of it, and at some point it will never change anymore. So now the algorithm works for what he thinks is the good version of beta. So for every stage S and every ordinal alpha bigger than the current version of beta, written by some universal U, you simulate a run of U for alpha step. And if at some point, for some ordinal between beta S and alpha, you find that the value is 1, and if beta S has changed, well, since the ITTM last wrote something, then you write alpha on the output tape. So at first, because you don't have the good version of beta S, you will write many ordinal alpha which are not the one you want. But eventually beta S will converge to the correct ordinal beta. And as it converges, also the ordinal you write here will also converge to and settle to the right ordinal. And ultimately, well, it has to settle to something which is not eventually writable if this value goes from 0 to 1 at some ordinal step which is not eventually writable. And then this would be a contradiction. And you have similar arguments for divergence. So here we show that if you have convergence up to sigma, then you must have convergence up to zeta, right? So if you have divergence up to zeta, you must have divergence up to sigma. So how do you show that? Well, you start some algorithm with some ordinal beta to 0. Then for every ordinal written by some ITTM U, some universal ITTM U bigger than beta, you simulate another run of U for alpha step. And if the value changes for some ordinal between beta and alpha, then you set beta to alpha, you write alpha, and you do it again. So this algorithm will eventually write some ordinal alpha such that this value does not change between alpha and sigma, because this is our assumption here. But then the ordinal alpha that we write, well, will be eventually writable, because it will also, at some point, we write this ordinal and it never changes. So it must actually be eventually writable. So the whole step of an ITTM at step zeta is the same than its state at step sigma. And in particular, it enters an infinite loop at step zeta. So we can deduce from this that lambda is actually not only the supremum of the writable ordinal, but also the supremum of some ITTM halting times. So the time at which some ITTM can halt. So indeed, if we suppose that some ITTM halts for some accidentally writable ordinal, right? Then we can run this ITTM for every ordinal beta that some universal machine accidentally writes. And whenever we find one so that it halts, we write beta. That then it must be, the halting time must actually be writable. If an ITTM writes for some accidentally writable, at some accidentally writable step, it must halt actually for at some writable step. And all the previous development shows that actually it cannot halt beyond some accidentally writable step, because if it hasn't halt by step sigma, then it will never halt. And this allows us to show that actually the writable reals are exactly the reals of L lambda, and same for the eventually writable with L zeta and accidentally writable with L sigma. So another very important notion dealing with ITTMs and the constructibles. So for some ordinal alpha and beta, we say that L alpha is unstable in L beta, and we write it this way. So basically, if any formula which is true, for any formula phi with parameter in L alpha, then L alpha satisfies this formula if and only if L beta satisfies this formula. So for any sigma n formula phi. So what model theories call elementary extensions, or so for some reason in constructibility theorists call it stability. And we have this theorem, lambda, zeta, and sigma, is the lexicography's smallest triplet such that L lambda is sigma 1 stable in L zeta, which is itself sigma 2 stable in L sigma. And you can show that sigma is not an admissible ordinal. So contrary to lambda and zeta, so this one is a bit peculiar, it's not admissible. But it is, however, a limit of admissible ordinals. So let me now talk a bit about ITTM and randomness. So Karl and Schlicht defined and started to study these notions. We say that a real X is alpha random if X is in no set with if it's no set of measure 0. I forgot that here, whose Borel code is in L alpha. So and we can try to define Martinov randomness in a similar way. So we say that as it is done like for proper Martinov randomness, we say that some open set U is alpha CE. Well, if it's a union of some cylinders for a set of cylinders which is sigma 1 definable over L alpha. And we say that X is alpha Martinov random if it is in no uniform intersection of alpha C open sets whose measure decreases to 0 sufficiently fast. So in order to study these randomness notions, we need to use actually the notion of projectum. So we say that alpha is projectible into beta, a smaller ordinal beta, if there is an injective function from alpha to beta, which is sigma 1 definable in L alpha, and in which case beta is called the projectum of alpha. So we have the following, which are equivalent for some ordinal alpha limit, such that L alpha is model of everything is countable, which is the case for all the ordinals smaller than sigma. So alpha is projectible into omega is equivalent to the fact that there exists a universal alpha Martinov test, which is equivalent to the fact that alpha Martinov randomness is strictly stronger than alpha randomness. So using this theorem, we can apply it to our three ordinal lambda, zeta, and sigma. So it's not very hard to show that lambda is projectible into omega without using any parameters. So basically, you consider, so any writable ordinal can be effectively assigned to the code of the ITTM which writes this ordinal. And as a corollary, well, most of the work done with delta 11, pi 11 Martinov randomness still work for lambda Martinov randomness, lambda randomness. In particular, lambda Martinov randomness is strictly stronger than lambda randomness, and you have a version of Chaitin's omega. The situation is different for zeta. Zeta is actually not projectible into omega. And as a corollary, well, zeta randomness coincides with zeta Martinov randomness, and some analog of omega for zeta randomness does not exist. And so for sigma, sigma is a bit more difficult to work with because it is not admissible. So it makes it uneasy. It's not very easy always to work with non-admissible ordinal because the intuition you have doesn't necessarily work. But you can show that zeta is projectible into omega, but using zeta as a parameter. If you don't use zeta as a parameter, if you use smaller ordinals, then it doesn't work anymore. So basically, basically using zeta, you can define like this function. You take the smallest, so having so this is a content of the tapes for some universal ITTM that you consider, and at step n, you look for the smallest alpha so that the n first cells for the run of some universal ITTM equals to the content of the cells at step zeta. And using this, you can show that this defines you some omega sequence of ordinal, which is cofinal below sigma. And using this, assign integer code to every accidentally writable ordinals. So, and now the most, in my opinion, is interesting notion of randomness for ITTM randomness. So we say, just like we define decidable class of reals, well, you define in a similar way semi-decidable class of real. So A is semi-decidable if there is an ITTM, well, which takes some oracle X in parameter and halts if X belongs to A, and doesn't halt if X doesn't belong to A. And we say that X is ITTM random if it is in no semi-decidable set of measure 0. So some other definition useful for the characterization to come. We say that X is low for lambda if lambda X equals lambda, low for zeta if zeta X equals zeta, and low for sigma if sigma X equals sigma. So basically X as an oracle cannot increase the smallest non-writable ordinal and so on. And we have this characterization, X is ITTM random if and only if it is sigma random and sigma X equals sigma. And you can also show that if and only if it is zeta random and sigma X equals sigma. So here is a summary of some results I mentioned. So we have that the lambda randoms are a strict subclass of the lambda Martinov random, which is itself a strict subclass of the ITTM randoms. The zeta randoms equal the zeta Martinov random, but these are a strict subclass of the ITTM randoms. And using the theorem above, the sigma randoms are a subclass of the ITTM randoms, and we can show that it is itself a strict subclass of the sigma Martinov random. Well, because here, basically the idea that we can use some parameters which are not necessarily eventually or writable, and this helps us improve our power. But with ITTM randomness, we don't have access to, and we have access to no parameter except the one we write ourselves. So, and the big question which remains is this inclusion here strict? So does there exist X which is sigma random, but not ITTM random? And the question actually is equivalent to this one. There exists set X which is sigma random, but such that L zeta of X is not sigma 2 stable in L sigma of X. So, and if this happens, actually, X increases, must increase sigma and also lambda and zeta. So it's not very hard to show that if X is sigma random, so a candidate to be ITTM random, then we must have this. We must have, it must preserve sigma 1 stability everywhere. So a presumably easier question is the following one. Does there exist any set X which preserves sigma 1 stability between zeta and sigma, but does not preserve sigma 2 stability? And already the answer to this question is, I think, quite hard, and at least for computability theorists, as it uses some techniques which are, well, which I did not know. I mean, technical, complex technique to work with a constructible universe. So there is a proof sketch by Cy Friedman of how to build such a real X. So basically, you would have to. So this is I think a very interesting process, because in order to build this real X that you will then use as an oracle within your ITTM, you need to completely abstract yourself from this machine model, and you have to go through objects which you cannot necessarily represent, which are not ordinal, which are not reals, but which are really sets of ordinal. So using some variant of co-enforcing for classes of ordinals, so you can build a subset A of zeta, so a collection of ordinals cofinal in zeta, such that for any extension of this set A, you have sigma 1 stability. And then you consider the specific extension which adds only zeros on ordinal bigger than zeta. And having this set B, then it has to kill sigma 2 stability, because B is cofinal below zeta, but not cofinal below sigma. So B as a set of ordinal preserves sigma 1 stability, but not sigma 2 stability. But we don't want a set of ordinal, we want a real which codes for this set of ordinal. And then there is a very interesting technique called almost disjoint coding, which has been used previously basically to code sets of ordinal by a real X. So the idea then to use some almost disjoint coding, so to encode all these ordinal into some X in such a way that you preserve sigma 1 stability like this. So maybe I'll skip on the details of the almost disjoint coding. So this is the forcing. And basically the idea is that if you're sufficiently generic, then you have a way, using your generic, which is a real, to decode all the ordinals that has been coded. Basically by checking a simple sentence. And using this, your set G, which is a set of real, can help you. The more and more you have ordinals which arrive that you accidentally write, your set G helps you to decode more and more the set A in such a way that at the end you have this equality. So maybe let me tell you a little bit. So I think this is interesting. How well was used disjoint coding, and when did it appear? So I think it's unclear to me who invented it. I think it's maybe Jensen and Solovey, or maybe just Solovey. So Beller, Jensen, and Welch, in a book like 300 pages proof called Coding the Universe, they showed something which I find quite fascinating. There is a model M of ZFC. So any model M of ZFC, so some author need add also here generalized continuum hypothesis, but in the proof I've seen from Cy Friedman, it doesn't need this hypothesis. So any model of ZFC can be considered as a submodel of the constructible relative to some real X. And this is like a two-step proof. So the big step is this one. So consider any model, you make your model of ZFC a submodel of the constructible relative to A as a proper class of ordinal. And then using only a single real, like a countable object, and using some very intricate and complex combination of iterated almost disjoint coding, with a single real X, you're able to decode all of A, which is a subclass of the ordinal. And of course, so I think it's a very fascinating thing here, that with a real, you can decode something which is not even a set. And you do it, of course, the information of A is not per se inside X, because A is much more than uncountable. It's like all the ordinals. But as you have more and more ordinal which become available, X is able like to decode, to check whether this ordinal belongs to A or not. So I think this is a very interesting thing, theorem. So this raises another question, which also I think is very interesting. So Sachs showed that a very well-known theorem from Sachs is that a countable ordinal alpha is admissible if and only if it is the smallest non-X computable ordinal for some X. And we can ask a similar questions for ITTMs using the versions of being non-computable for ITTM, and we have 3 of them. So if alpha, beta, and gamma are countable ordinals such that L alpha is sigma 1 stable in L beta, which is sigma 2 stable in L gamma, can we find a real X relative to which this alpha is the smallest non-writable, beta is the smallest non-eventually writable, and gamma is the smallest non-accidentally writable relative to X? And I conjecture that, yeah, even though it may be very hard, we should be able to work it out using almost disjoint coding. And so I will, I think I will skip the 2 next slides because we're running out of time, and end my talk with this summary here of the 2 questions. I think the 2, I don't know, I think 2 very interesting questions about ITTM, Turing machines and randomness. So does there exist, can you separate sigma randomness and ITTM randomness? And given 3 countable ordinal, so that the L alpha is sigma unstable in L beta, which is sigma 2 stable in L gamma, can we find a real X relative to which these are the ordinal corresponding to Turing machines? Yeah. And this ends my talk. Thank you very much.
Thank you, Benoit. Do you think we have time for a question, maybe, if someone has a question?
Sure. Please ask questions.
Yeah, just unmute yourself and ask your question if you have one.
Benoit, I have a question about the first question on your slide.
Yeah.
So do you already know how to do like each of these individually, like the lambda and the C and the sigma? Like say, let's say you have alpha, beta, and gamma, and let's say you just need alpha to be equal to lambda to the X, but you don't care about what beta and gamma.
No, I think these are quite intricate. So I guess there are easy cases. But in general, no, this is still a work in progress, which did not progress very far so far. But I think this, Yeah, these are quite intricate, and so no, I haven't really focused on increasing lambda. So except in very special cases, but I think the most difficult part, which is what I focused so far on, is this one, the sigma to stability. But so it might be that the conjecture is false and some weaker assumptions are true. But no, so far I don't know how to do anything. It's a very I don't know, bold conjecture. Like I don't know anything. It
Right.
might, but,
okay, thank you.
Any more questions? Yes, I think we have yet another question.
Yes, if I can.
Yeah.
Sure.
I'm puzzled a little bit by the model you are using.
Yeah.
The whole theory evidently is based on the fact that you represent ordinals by writing a well-ordering by some coding. Now, for example, if you look at your proof that this capital sigma is accidentally writable,
Yeah.
you construct a machine which will generate a number of ordinals, add them up, and write that, and then compute forever.
Yeah.
And you said that at some point it writes capital sigma, and subsequently it must write something other if it's not.
So it does not take capital sigma. Capital sigma is the smallest non-accidentally writable. So no,
Yes,
right.
but you had
Accidentally
some.
write. So you mean zeta maybe?
Sorry.
Sorry, do you want me to come back to?
It was rather in the beginning.
Yeah. Here, so to write lambda, for instance.
To write lambda, that I understood. And then you had zeta, and then you had sigma. And I think you had a similar construction for sigma.
Oh no, for sigma, I don't write anything.
Oh. And for zeta, yes, maybe it's then a question about zeta. It writes a set of ordinals, and it adds them up, and then it goes on computing forever. But it can never write something which is larger than zeta, because zeta is the largest thing it could evidently have written.
Yeah.
But it can also, by this construction, not write down something which is smaller than zeta, because it's the sum of things it has already written. So that goes against my intuition.
I'm sorry, I did not get the question. So you're saying that you see some contradiction in the...
In this construction.
Because you could, so there is a construction which show how to accidentally write zeta.
Yes.
You think using a similar construction, we could show that, what? Which would arrive at a contradiction?
Yes, that it seems that by this construction it becomes eventually writable.
Oh, zeta.
Zeta, because if this machine goes on computing,
yeah.
It must produce something different, but it cannot be a larger ordinal, because that large ordinal would then be eventually writable. And it cannot be smaller, because it is the sum of things it has written previously, so that sum should never be decreasing.
I'm not sure. So this algorithm clearly, so the issue with making zeta eventually writable, so using this algorithm, basically you look at all the ordinals which are written at some point on the tape. And so splitting, you split the tapes on omega many parts, one for each machine. And you run all these machines and they write, some of them write ordinals and some don't.
Yes.
Ordinals, you can recognize that it is an ordinal and then sum them all. And for all those which write eventual ordinals, which in some eventual way, like at some point the ordinal is there and doesn't change, then it sums them all and writes something bigger than the smallest non-eventually writable. But then the ordinal you write, I don't see a way to make it itself, so then it will change forever. The ordinal zeta you write, using this algorithm,